Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. Welcome to the final topic in a differential calculus course. This is also a good topic to start an integral calculus course with as well, because it would remind you of all the stuff you learned in the last chapter of your differential calculus class. So in your next semester, if you're going to take integral calculus, I recommend coming back to this video to kind of review some topics, because the stuff in this video is going to, or in this series of videos, this video and the next one, is going to be very important for you as you move forward. So this video specifically is dedicated to something called the substitution rule, and specifically the concept of it, the theorem, and the proof itself. And then we'll do a ton of examples in the next video. But let's start with a motivating question. Motivating question, I guess. Consider the following integral: the cosine cubed of theta, sine of theta, d theta. Again, this is an indefinite integral that we learned from the last video series. So indefinite integral, which normally indefinite integrals will return the antiderivatives. So you often ask yourself when you see an indefinite integral, what would you take the derivative of to arrive at the integrand? Well, this specific indefinite integral, you might be able to guess your way to what you would take the derivative of to arrive at this, but that would be strictly a guess. You really do not know offhand very quickly the antiderivative of cosine cubed of theta, sine of theta. That is, you do not know what you would take the derivative of to arrive at that. And that's really the answer to this part A here. Do you know the antiderivative of the integrand? Heck no, not offhand. So I'm just going to put a big old no there. We do not. Nope. So now, if I'm going to demonstrate the substitution rule, if we allow you, maybe before I begin that, maybe I should just remind you of something you've done for years. Back in algebra, and when I teach pre-calculus and trig and algebra and stuff like that, I always do this. You dealt with equations like this. Well, not like that, because that looks like a mess, but you dealt with equations like this. X squared plus x being squared plus 5 times x squared plus x plus 6 is equal to 0, or something like that. And this, when you were in algebra, the advice should have been from your instructor, do a substitution. If you see patterns, do a substitution. It's very nice to simplify things. So what we would do here is we would let u equal that x squared plus x. It's called a u substitution. And if you do that, then you're really looking at u squared plus 5u plus 6 is equal to 0. And look how nice that trinomial is versus the original equation. This equation right here is much easier to deal with. And by the way, it factors, right? U plus 2 times u plus 3, that will equal 0. Therefore, either u is equal to a -2 or u is equal to a -3. Now, as I would tell my students in an algebra course, you didn't start this problem in the world of u. You started in the world of x. And so you have to resubstitute back into the world of x. That's a very important step. You resub back into the world that you originally started in. Well, we know that u is equal to x squared plus x. So we have x squared plus x is equal to a -2, or x squared plus x is equal to a -3. And then you now arrive at, well, at least one nice trinomial to solve. The other one's not nice to solve, but at least the leftmost one is not too terrible to solve. Actually, I think they're both kind of bad to solve, but anyhow, it doesn't really matter. The fact is, you arrive at these two quadratic equations, and from that point, you would solve them out, and you'd find out what x is. that's the advice you would get back in an algebra course. That advice still holds to this day. So if I see an indefinite integral, like this guy right here, a substitution might simplify this quite significantly. And we call them U substitutions because we're using the letter U. So if we let U equal the cosine of theta, let's go ahead and just write this down below. I'm going to actually even write the words let. So let U equal the cosine of theta. Well, if you only do that, your integral would be broken. Because if you do that, the integral of cosine cubed of theta times the sine of theta, d theta, it would be the integral of U cubed sine of theta d theta. And notice you have a mixture of variables within this indefinite integral. That's a big no-no. You do not want that. I should be very clear about this, that it is technically impossible for you to integrate that at this level, but it is okay to write that as a stopover. The problem with this stopover is that we're integrating with respect to theta, and we don't want to. You want to change completely into the world of U. So you'd like to know what is the relationship between d theta and du. And recall from your differential calculus course that if y is a function of x, then dy is defined to be f prime of x dx. That's the differential of y is defined to be the derivative of that right-hand side times the differential of the independent variable. Well, in this case over here with our function, we let u equal the cosine of theta. Writing the differential of u, du, we get negative sine of theta, that's the derivative of the cosine of theta, and then times the differential of the independent variable, d theta. This tells me that when I do this substitution, and I cross this out in red over here because that can't be your final answer. So it's okay to write that ink that's underneath those red crosses there. It's okay to write that as a stopover, but it's not okay to stop there. But what we can do is we could say, oh, notice I have u cubed sine of theta. Let me write that in blue. Sine of theta d theta. And notice that sine of theta d theta can be replaced by a negative du. I just multiply both sides by a -1. And so I will go ahead and go back to our indefinite integral and transform completely into the world of u by replacing that blue ink, the sine of theta d theta, with a negative, which I'm going to pull out front, negative integral of u cubed du. Remember, negative du can trade out sine of theta d theta. So that sine of theta d theta becomes a negative u du. And now the question really becomes, hey, what is the antiderivative of u cubed? And you would appropriately respond u to the 4th over 4 plus some constant c. I would say absolutely yes. And then I would say, hey, did we start this problem in the world of u? Just like I would ask my algebra students, did we start this algebra problem right here in the world of u's? And they would say, no, we didn't. And I would say, then in the end, make sure you resubstitute. Just like my algebra students, you're going to resubstitute in the end. So the next step, which I'll write right there, is the step to resub. Resub. And this, remember, u, off to the left-hand side here, we allowed to be the cosine of theta. So this is going to be the negative cosine to the 4th power of theta all over 4 plus some constant c. That is what you would take the derivative of to arrive at this integrand. That is the substitution rule. Well, that's an example of using the substitution rule. I'm just motivating it here. So again, part B was let u equal cosine of theta and then take differentials of both sides. So that was actually the part B right there. And then substitute these in, that's part C, and see if you can simplify, which we can. We started with an impossible indefinite integral. By making a wise choice for a u substitution, we were able to actually integrate this. So let's talk about what a wise choice means. Well, this will require us to actually see the theorem. So the substitution rule for indefinite integrals. If u is g of x, or if u equals g of x, is a differentiable function, because you need to take its derivative. You actually see right here that we took the derivative of some g, so g has to be differentiable, okay? Whose range is an interval I, and f is continuous on that interval I, then the integral of f of a function times g prime, or that, in other words, that function's derivative dx, that can be replaced by the integral of f evaluated at u times du. Now that seems really, really weird when I say it that way, but the truth is you're looking for a function in your integrand here. This is the integrand. You're looking for a function in there whose derivative is also there. So notice I have a function that's g of x, and I'll call that u. Notice that the derivative of u, or the differential of u, which is g prime of x dx, is also in this integrand. So essentially I'm looking for a function whose derivative is also in the integral. Now, this is a rule of thumb. In reality, it's not always going to be that easy. And you may not even think that's easy, honestly. But in reality, it's a little bit more of a heuristic method to figure out what to allow u to be for that u substitution. But let's go ahead and prove it, and then we're going to use it. Actually, you know what? I think it might be better to use it and then come back to this and prove it. And this example that I have here, it's generally a very, very nice, simple opening example. Integrate the sine of pi t. Now, you may be able to see very quickly what the antiderivative is, but generally what I like to tell my students is, if it's not just sine of x, because you might know quickly offhand the antiderivative of the sine of x, if it's not exactly sine of x, but instead in this case it's sine of pi times your variable, then you're going to have to substitute. You want to simplify this statement so it is like a sine of x. So we're going to go ahead and we want to replace that picture right there with just a single variable. So we're going to let u be pi times t. Now, when we transform this integrand into the world of u, we also need to transform its differential into the world of u as well. Because if I were to just write, oh, therefore, this is the integral of sine of u, I would still have this dt hanging out, and I can't integrate that. They're two totally different variables. It'd be like me saying actually, this is a good way to think about it. One variable is speaking one language, the other variable speaks a completely different language. They cannot communicate without a translator. And the translator is right here. All we need to do is find out what du turns into. And that, remember, if you take the differential du, it's going to be the derivative of this right-hand side. Well, the derivative of that right-hand side is just pi times the differential of the variable on that right-hand side, dt. So I know that dt, this specific dt right here, can be replaced by du over pi. That's what dt can be replaced by. Now, initially, when you're introduced to the u substitution method or the substitution rule, most instructors and professors will always solve for their dx, dt, whatever this differential here is. But in the long run, you're not really going to do that. But for right now, we're going to go ahead and just do that because mathematically, it's a little bit easier to see what you're doing. So I'm going to replace this dt with this. So our integral, transforming completely into the world of u's, is going to be sine of u du over pi. And that pi can be brought out front, so it's just 1 over pi integral sine of u du. And then you ask yourself, what would you take the derivative of? Remember, that's what we've been saying this entire time. What would you take the derivative of to arrive at the integrand? That's what I have written off to the right-hand side there. And you would take the derivative of a negative cosine, right? That's usually something that throws people off. But remember, you can always check your work here by taking the derivative of this. You should arrive at 1 over pi times sine of u, this picture right there. But did we start this problem in the world of u? And the answer to that is no. We have to transform back completely into the world of x. Luckily, right here, we have what u is equal to. U is just pi t. So I will say this is equal to a negative 1 over pi cosine of pi t, and then plus c. And that's it. We've done our first u substitution problem completely through. It was very simple, kind of obvious substitution because we didn't want to integrate sine of pi t. We just want to integrate sine of something, that a single variable. So we let u equal that pi t. Sometimes it will be that obvious. Hey, take, that looks overly complicated. Simplify it by calling pi t a picture. That's perfectly fine. Sometimes it won't be so obvious. Now going back to the theorem here and doing the proof, we're going to suppose the antecedent. That is, we're going to assume all this stuff I'm highlighting. I'm not going to bother rewriting it. I'm just going to assume that that's been stated. So we're going to let u equal g of x be a differentiable function whose range is an interval I and f is continuous on I. Okay, so we start with that. And since I have the ability to pause the video and write things out, I just went ahead and wrote down our assumptions. We're going to let u equal g of x be a differentiable function, and we're going to suppose that f is continuous on the range of g. Well, since f is continuous, we can actually state that it has an antiderivative. We're going to go ahead and call this antiderivative capital F, just like we have been all along, which basically means that capital F prime is equal to little f. That is, the derivative of the antiderivative just becomes the regular old function again. Also, the derivative with respect to x of capital F of g of x, that composition, by the chain rule is going to be f prime of g of x times, well, g prime of x by the chain rule, right? But we know that f prime, remember that notation, f prime, since capital F is the antiderivative of little f, the derivative of capital F can be replaced with little f. So this is the same thing as little f of g of x times g prime of x. What does this mean? Well, it means if you say I took the derivative of something and it arrived at this, the something you took a derivative of is an antiderivative of this picture. That is, let me write this down. Capital F of g of x is an antiderivative of little f of g of x times g prime of x, which means that if you were to integrate, do an indefinite integral of this f little f of g of x times g prime of x dx, that should turn into that capital F of g of x. So again, this implies the indefinite integral of f of g of x times g prime of x dx should turn into a capital F of g of x. Now remember, we also have the constant of integration, so I'll just say plus c. Now let's compare with where we want to end. So we want the integral of little f of g of x times g prime of x dx to turn into some f evaluated, the integral of some f evaluated at u times du. Well, that's actually not too terrible to do. All you need to do is let u equal g of x. So let's go ahead and do that. If we let u equal g of x, then du, the differential of u, is g prime of x dx. Okay. And therefore, we arrive at the integral of f of g of x times g prime of x dx. That can be replaced with the integral of f evaluated at u, because that's what g of x is, and g prime of x dx, that g prime of x dx, which I'll highlight both here and here, can be replaced with a du. And remember, this integral is actually f evaluated at g of x plus c. But remember, g of x is u, and so we have f of u plus c. Now, I kind of went a little bit more than I needed to on that one, honestly. All I really wanted to prove was that this equality was true, but I just wanted to kind of throw everything else in there as well. But that middle part is what's important. That's actually the proof of the substitution rule for indefinite integrals. Again, using it is an art form. It's not something like, oh, always do this thing. It's going to be an art form. It's very heuristic. So let's try to use it again. Let's take this indefinite integral of dx over 1 minus 2x. And generally speaking, when people face indefinite integrals or definite integrals, they get a little bit weirded out when they see a dx in the numerator. All of that means is you just moved this dx that was originally not in the numerator, but multiplying on the outside, you just move that in. But if you prefer to write it this way, which I personally prefer to write it this way, then please do. That's totally fine. Now, when you look at this integral and you ask yourself, let me go ahead and just say, what do you take the derivative of to arrive at the integrand? You might not be able to figure that out very easily. And even if you might be able to finagle your way to a possible antiderivative, it might take a little bit of care in doing so. So instead of taxing yourself and trying to do everything all at once, it's much better to do it step by step and just say, well, I know what the antiderivative of 1 over x is. Oops, I meant to write. If it was just an antiderivative of 1 over x, I could totally do that. So I would love to replace this picture right here with not x because it's being used, but a different letter, which I will call u. Let me fix that. So I'll go ahead and say here, let u equal 1 minus 2x. So that denominator, I'm just going to replace with 1 minus 2x. Now, when I transform into the world of u's, I need to get rid of this dx as well. So let's go ahead and say the differential of u is the derivative of this right-hand side. That'll be a negative 2 times the differential of the variable on the right-hand side. So du is a negative 2 dx. That is, wherever I see a dx, I can replace it with a negative 1/2 du. Now I'm ready to do a full substitution for this problem. I'll just grab this here. I'll say this is equal to the integral 1 over, instead of 1 minus 2x, I'm going to call that u because that was our substitution. And dx, well, that's going to turn into a negative 1/2 du. Obviously, I can pull the negative 1/2 because it's a constant. I can pull that outside of the integral. And the antiderivative of 1 over u, which is one of the ones I told you in a previous video is one of the most important antiderivatives you can face. This antiderivative is going to be the natural log of the absolute value of u. Be very careful there. That absolute value is incredibly important. And then don't forget we have plus a constant of integration. At the final part here, you should note you didn't start in the world of u. You started in the world of x's, so you should resubstitute in the end. Grab this guy right here and just plug it into your final answer. That'll be a negative 1/2 natural log absolute value of 1 minus 2x and absolute value plus c. And there you go. That is the full antiderivative of 1 over 1 minus 2x. Or in other words, the indefinite integral of dx over 1 minus 2x is equal to negative 1/2 natural log of the absolute value of 1 minus 2x plus c. So you could kind of see that antidifferentiation or integration is more complex than differentiation itself. Differentiation is pretty straightforward. Anti-differentiation, it starts becoming an art form. You start having to kind of make these little changes partway through and whatnot. So let's see, there's another theorem, and then we'll do an example, and then we'll be done with this video. And we're going to have a second video with a ton of examples in it, but I want all the theorems in this video. And the last theorem in the course is just the substitution rule for definite integrals. Remember, we just did the substitution rule for indefinite. Now we're going to do the substitution rule for definite integrals. If u equals g of x is differentiable on the closed interval from a to b, and f is continuous on the range of g over that interval, then the integral from a to b, this is almost identical to the substitution rule for indefinite integrals. The only difference here, in fact, let me go ahead and just showcase this by erasing. I use white ink here. So if I were to erase those out of here, what you're looking at is the substitution rule for indefinite integrals, right? But once I put limits on there, then I need to have corresponding limits here. Well, because we are allowing u to equal g of x, if somebody said I'm integrating from x equals a to x equals b, well then when we transform into the world of u, everything else here, by the way, is from the substitution rule for indefinite integrals, but the limits are the only thing we really need to talk about. If somebody says, no, transform into the world of u's, where we're going from x equals a to x equals b, and u is equal to g of x, well, then the lower limit, which was u evaluated at g at a, because x is equal to a at the lower limit, we're now integrating from u equals g of a to the upper limit. Just plug x equals b into this relation and you'll integrate to u equals g of b. That's really kind of the proof. I don't really have to do anything else. That is literally the proof. So let's go ahead and see this in action. It's not as bad as what the theorem looks like. It's actually pretty okay to do, but I'll have a lot of advice in the next video on tactics. But initially, let's go ahead and tackle this. Integrate the definite integral, or evaluate the definite integral from 1 to 2 of e to the 1 over x squared dx. Now you take a look at that, and it looks like a really complex integral, because you do not know offhand, likely, what you would take the derivative of to arrive at that. If you do, good for you. I don't care. What I do care is you know how to use the substitution rule. So you're going to look through this integrand here for a pattern. And the pattern you're going to look for is a function whose derivative is also here. Now, if I look through this entire integrand here, you can see that one option is 1 over x. I could say, well, is the derivative, or I could ask, is the derivative of 1 over x roughly in this integral? Not that is it exactly in the integral, but is it roughly in this integral? Remember, you're asking yourself, what do you want to take the derivative of to arrive at that integrand? And in this case, we just don't know. So going through this, note that maybe I should write this off to the right-hand side as well. Is the derivative of that 1 over x somewhere in the integrand? And roughly it is. You don't need it to be the exact derivative because plus or minus signs don't matter. But what does matter is you basically have its derivative in there. And it is true. The derivative of 1 over x is a negative 1 over x squared. Well, I have a 1 over x squared. The 1 over x squared is this piece right here. So let's go ahead and try that substitution. And by the way, the substitution rule is a rule where you're going to try some things that don't work and you'll have to restart. That's totally fine. So I'll start with let u equal 1 over x. Well, then the differential of u is going to be the derivative of that right-hand side, just negative 1 over x squared, times the derivative of the variable, or sorry, the differential of the variable on that right-hand side. Notice in our integral here, we're integrating from x equals 1 to x equals 2 of e to the, well, maybe I should write it this way, of 1 over x squared times e to 1 over x dx. I write it that way so you can easily see that, yes, I actually do, whoops, that was supposed to be a highlighter. I actually do have a 1 over x squared in my integrand. And I have a dx. So that's pretty cool. I'll keep this highlighted term or factor on the right hand side, and I'll just move the negative to the other side. So this would imply a negative du can be replaced with a 1 over x squared dx, or saying it the other way around, if I have a 1 over x squared dx, which I do, I just highlighted the 1 over x squared dx in our ink up here. So because of that, we can replace that with a negative du. Now, a couple things you need to note here. With definite integrals, there's a little teeny bit of extra work you're going to have to do. This is an integral from x equals 1 to x equals 2. And we're not going to be integrating with respect to x in a moment. At least I know that wherever I see a 1 over x squared dx, that highlighted ink right here, I can replace that with a negative du. Notice I put the negative out front just because I don't want it in my way. The rest of the stuff that I didn't highlight, e to the 1 over x, is e to the, instead of 1 over x, u. So this is the complete substitution, except that we need to substitute out the limits of integration as well. Now, this is, your instructor might be different than me, or your instructor is definitely different than me, but your instructor may not require you to do this, but I require my students to transition completely out of the world of x and into the world of u when you integrate. There's only a few exceptions where you probably don't need to, but this is one of those cases where I highly recommend you move out of this world. So I'll write my thought process over here. When x is equal to 1, in other words, we're at the lower limit, according to this formula right here, u is also equal to 1. And when x is equal to 2, which is our upper limit, u is equal to 1 over 2. So this is my transformation. Instead of x equals 1 and x equals 2, I'm going to have the integral, negative integral actually, from u equals 1, because that's what u is when x is 1, to u equals 1/2. E to the u du. Now you say, wait a second, that's written in the wrong order. You're starting at 1 and ending at 1/2? 1/2 is smaller than 1. You are fully allowed to flip those limits. Remember, when you flip those limits, a negative will pop out. So, whoops, when I flip the limits, there we go, a negative will pop out. So we had a minus sign already, another minus sign will pop out, because that's what happens when you flip limits of an integral. You remove a negative from the situation. Or you could have just said, when I flip those limits, this negative will bleed into this integral and disappear. Your choice. I don't really care. It is actually true. So in the end, you get something like this. Now, question. What would you take the derivative of to get that simple e to the u? And you would say e to the u. And I would say you're absolutely correct. And you're evaluating that from u equals 1/2 to u equals 1. In other words, you get e to the first minus e to the 1/2. That is the area underneath this curve right here from x equals 1 to x equals 2. Notice two things here. Very important, because at this point, I've taught this course long enough that I know at this point, there are these big dominating questions that people have in their minds, and they need their answers. Even if it's not in your mind, you're going to think about it later on. So the two questions I will often get: where is the c? Right? You've been dealing with indefinite integrals for such a long time now. When I say such a long time, I mean like a section. And you know, with indefinite integrals, they pop out this constant of integration. So where's the c here? Well, this was not an indefinite integral. Indefinite integrals pop out a C, but definite integrals don't. So do not worry about a C popping out here because definite integrals return constants. And yes, I know C is a constant, but in reality, what you're really doing here, if you really want to see what happened to the C, you could say, oh, let me erase this for a moment. You could visualize it this way. The antiderivative of e to the u is e to the u plus c, and you're evaluating that from u equals 1/2 to u equals 1. And when you plug in 1, you get e to the 1 plus c minus, and when you plug in 1/2, you get e to the 1/2 minus c, and the c's cancel. So that's a way you can kind of think about that. Although that's, you don't need to do that, but it is true. The constants will actually cancel. So with definite integrals, the constants of integration disappear because they cancel. So I will just say that the c canceled out, and definite integrals do not result in arbitrary constants of integration. So that's one of the first things that students will ask, like, where's the c on this? What happened with that c? I'm really very curious, or something like that. Okay. The second thing, and I'll go ahead and zoom in for this. Because we did a u substitution, when do we resubstitute back into the world of x? Well, this is the nice thing about definite integrals. When you're working with a definite integral, your final answer is a constant. It doesn't have any variables at all. So if you do a u substitution, if you followed my advice and transform the entire integral into the world you're substituting into. So this integral right now is not transformed entirely, but in the next step, you see everything's in terms of u's. Once you transform into that world entirely, you end up working all your mathematics in that alternative world, and the answer you get suffices in both worlds. This constant is the constant answer in both worlds. Had you left everything in x, or had you done everything in u's. So there is no need with definite integrals to transform back into the world of x. So many times I'll see students in Calc 2 that do that. They'll transform back into the world of x when they shouldn't. It's a waste of time. If done properly, you should never have to transform the result of a definite integral back into the world of x. What I mean when I say if done properly is that if you have transformed everything step by step into the world of u, then your final answer is just a constant and you don't have to transform anything back. That is very important, very, very important. So I know a lot of students are taught by lazy instructors. I will say that, I'm okay with that, who say, well, you don't have to transform, you know, as long as you transform your limits back in the end or something like that. That leads to too many mistakes. So I don't even teach that. Well, that's kind of a lie. I teach it if you're dealing with inverse trig functions every once in a while. But that's neither here nor there. You don't have to worry about that. Okay, so we're done with this video. In the next video, we'll tackle all the substitution style problems we can.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.